Today I'm going to be solving this combined loading problem, and we're going to solve it for the principal stresses and maximum shear. Just double check, that's yeah, the maximum shearing stress. Shearing stress. All right, and we're doing this at point H, which is right here. First step is to cut the beam at H. And I'll draw what that looks like. That's really bad drawing. All right, and then we move the axes to the cross section of the cut plane. This is X, Y, and Z. And then now we're going to find the resultant forces at the cross section. You have a negative 3 kilonewtons, a negative 2.5 kilonewtons in the Z, and then I guess I don't have enough space, so I'll draw it this way. Negative 0.5 kilonewtons, in the Y. So I'm going to solve for the resultant forces in the X, Y, and Z, and the moments with summation of forces. So summation of forces in the X equals 0 equals a normal force in X minus 0.5 kilonewtons, which gives the normal force in X as 0.5 kilonewtons. Summation of moment at X is the resultant moment actually, it would be, but since the 2.5 kilonewtons goes through the x-axis, the 3 kilonewtons goes through the x-axis, and the 0.5 kilonewtons goes through the x-axis, the moment at x is 0. So then moving on to the summation of forces in the Y, it'll be a shear force as a result, and it's minus 0.5 kilonewtons, which gives shear at Y of 0.5 kilonewtons. Looks like I got ahead of myself on X. Let me just fix that. Instead of 0.5, it's actually negative 3 kilonewtons, which would have the normal force at X of 3 kilonewtons. Summation of forces, not summation of forces, summation of moment at Y equals resultant moment at Y, and then the 3 kilonewtons goes through the y-axis, the 0.25 is parallel to the y-axis, Y, Z, and then X. Dang, that's really bad. But this force, the 2.5 kilonewtons, will cause a moment which is counterclockwise, so positive, 2.5 kilonewtons times the distance away, which is 150 millimeters, or 0.15 meters. Moment of y becomes negative 0.375 kilonewtons per meter. And just to write it down, moment equals force times the distance away from the axis. That's in consideration. Summation of forces in the z is the reaction force, and then minus 2.5 kilonewtons. Vz becomes 2.5 kilonewtons. Lastly, summation of moment. Oh, forgot to put these. They do as well equals 0. The resultant moment. And then again, 2.5 kilonewtons is parallel to the z-axis, and the 3 kilonewtons goes through the z-axis, so they both don't contribute to the moment, but the 0.5 kilonewtons does, and it causes clockwise, which is negative 0.5 kilonewtons times the distance away from the axis, which is 0.15 meters. So the resultant moment around the z-axis is 0.075 kilonewtons times m. Okay, I'm going to circle these so that we can find them. When we need them later. Okay, so before we look at each one individually, let's calculate the area of the cross section, which has a base of 40 millimeters and a height of 20 millimeters. Do this, y, z. Okay, so the area is just base times height, or 40 millimeters. I'll write this in meters to keep it consistent. 0.04 meters times 0.02 meters, or 8 times 10 to the negative 4 meters squared is the area. I'm also going to go ahead and calculate the inertia for y and z. Inertia for z is 1/12 base times height cubed, the base being 40 millimeters and the height being 20 millimeters. That turns out to be 1/12 times 0.04 meters times 0.02 meters cubed. The inertia of z is 2.667 times 10 to the negative 8 meters to the 4th. And then let's calculate the inertia of y as well, which is 1/12 base cubed times height. 1/12 times 0.04 meters times 0.2 meters, and then this is cubed, the base, and then this becomes 0.067 times 10 to the negative 7 meters to the 4th. All right, now we are ready to start looking at the individual resultant forces and moments and how they contribute to the overall, their overall effect on H. So let's start with the resultant of X, which is axial, and we're going to look at it from the Y direction. Looking downward. Or I guess I'll draw it the other way so that we're just looking at the cut part. X direction and go the other way, the Z direction, or the axis. And then, so we have a force here, a normal force of X of 3 kilonewtons. 3 kilonewtons. And then this is going to cause an axial stress. The equation for that, sigma x equals the normal force in X direction over the area. Normal force is 3 kilonewtons. The area that we found up here is 8 times 10 to the negative 4 meters squared. This is going to become sigma x is equal to 3.750 megapascals. All right. Moving forward. Mx is 0. Remember we found it up here. 0, so it does nothing. Our y is our next resultant. And we're going to look at this from the Z direction. And it is transverse shear. Z direction. You have X going this way and Y going upward. And our point is going to be right there. Okay. We have shear force going upward of 0.5 kilonewtons. And then transverse shear, we're going to look at cross section. Z and Y. And H is right there. Okay. The normal axis for this is going to be the Z axis. And the equation is tau equals VQ over IT. Q equals A prime Y prime. But in this case, Y prime is the area from the point of interest to the outermost point of the shape. And in this case, it's on the outer edge. So A prime is 0, which causes Q to be 0. And the whole thing is 0. The transverse shear is 0 because A is 0, which makes Q 0. If Q is 0, then tau is 0. And this makes sense because the stress distribution for transverse shear, or VQ over IT, is a parabola with zeros at the endpoints, which is H, and at the neutral the axis, it has a maximum transverse shear. But since we're on the endpoint, transverse shear is 0. Okay. Let's look at the moment at Y. We can look from the Z direction again. And this is going to be a stress. In the X direction. Or keep drawing them backwards. X, Y, and H. But if you look at the diagram I drew above, actually I'm jumping ahead of myself. Let's write down the equation. Sigma equals the moment, in this case Y, times Z over I, or inertia. Looking at this diagram here, the cross section, you can see that H is at point Z equals 0. If Z equals 0, this makes sigma equals 0. So just like Ry, My also doesn't cause anything to happen. And this is because H is on the outer edge and has a Z of 0. Okay. Moving forward, the resultant at Z causes transverse shear we'll look from the Y direction. Let me just double check this. Okay, Y downward. Try this. X and Z. H is right there. And transverse shear is coming down. Oh, sorry, this is Z at 2.5 kilonewtons is the resultant in the Z direction, or VZ. Let's look at the cross section one more time. Y, Z, and it is right there, right? So the normal axis in this case is going to be the y-axis. And since H lies on the y-axis, this means that this is going to be our maximum transverse shear. Equation T equals Q, or tau equals VQ over inertia around Y, and then the thickness. Okay. Q equals the area which, let's look back at the initial problem. It's 40, okay. So, whole thing is 40 millimeters. Height is 20 millimeters. That means, and we'll just say this is A prime, right? Okay. So that means this right here, the width or height of A prime is 20 millimeters and 20. So I'll just write Q equals A prime Y prime. A prime equals 20 millimeters. I gotta keep it in meters. Keep all my units the same. So 0.02 meters squared. This becomes 4 times 10 to the negative 4 meters squared. And then y prime is the distance from the neutral axis to the middle, or the centroid, of A prime, which in this case would be half of 20 millimeters, which is 10 millimeters, 0.01 millimeter, or just meter, 0.01 meters. So then Q, I'm going off the page, but would be 0.01 meters times 10, or times 4 to the negative, to the 10 to the negative 4, I can't speak today, 0.1 meters times 4 times 10 to the negative 4 meters squared, which results in Q being 4 times 10 to the negative 6 meters cubed. Okay. V in this case is 2.5 kilonewtons. Let's see, tau equals 2.5 kilonewtons times Q, which is 4 times 10 to the negative 6 meters cubed over I around Y, which we solved already to be 1.067. Must write another I. 1.067 times 10 to the negative 7 meters to the 4th. This is multiplied by the thickness, which is 20 millimeters, but also 0.02 meters, tau, and this is on xz because h is on the xz plane, so that's where the transverse shear must be, is 4.6875 megapascals. Okay. Finally, let's look at the reactional moment at Z. That causes stress at X. And we'll look at it from, let's see, moment of Z. We can look at it from the Y direction as well. All right. This is, let's look at the cross section again. And this is y, and this is h. Neutral axis is here. Sigma x, the equation for this. Let's see what it was back here. Okay. It's actually the same as the one down here. It would be mz times y over I y. Or actually, it would be iz. Okay. Moment would be, what is it? Positive or negative? Okay, positive. So then it's going to be going counterclockwise. 0.07 kilonewtons. Kilonewtons times meters. I just realized that I didn't draw this one. Let's be going clockwise. I know it doesn't matter, but just for sake of completeness, kilonewtons times meters, and then this one was 0, obviously. Okay. So we get, okay, 0.075 kilonewton meters times y, which in this case would be 10 millimeters over iz, which is 2.667 times 10 to the negative 8. Let's see. Yeah, meters to the fourth. That's right. Meters to the fourth. This will be 28.12 millimeter or megapascal. Okay, this is going to be in tension. Okay, and an easy way to know if it's in tension or compression: draw a diagram. Run the neutral axis here, I guess. If it's coming this way, the moment, it's going to be compressing here, compression, and tension. Anything above, tension. Anything below, compression. And it makes sense. It's pulling this down, and while it's pulling this half down, it is compressing the lower half. But since we're on the top, did I draw this wrong? One second. Oh, I did draw it wrong. Moment around this. We're gonna have to look at it from the y-x, so from the x direction. Sorry. Or from the z direction, right? For this one at least. It's my mistake. X direction going this way, Y direction going up. Here we go. Okay, this makes a little bit more sense now. Good catch. I'm gonna draw it on the other side as well. Okay. We go like this. Okay. And then, of course, I did it the wrong way here. But, you know, if this was mirrored and this was H, it'd still be in tension, right? You're pulling down, it's going to be in tension. Okay? This is in tension. Now it's time to combine them all. This one is in compression. Just the way the force is coming off, it's pushing out. It's going to cause a compressive because they're both pushing each other. From here, you can see it, but they're both pushing each other. It's going to be a compressive force. So this is C for compression, or actually, I'll just make this a negative to keep it easy because we're going to have to add the two sigma x's together. Summation sigma x equals this one, which is positive because it's in tension, minus 3 points. Where did I put it? 3.75. 75. You get us when added, or when subtracted, I guess. The total is going to be a tensile stress of 24.373 megapascals. All right. We only have one transverse shear, so we'll just bring this down. Okay. Now we can find the principal stresses. Or I guess we can do our stress blocks first, but we kind of already solved it. X, X, Z, and lastly, our ZY. ZY. All right. So in X, it's going to be tension of 24.373 megapascals. Same here. 24.373 megapascals. It's going to appear on transverse shear. It's only going to appear on our XZ plane. And it's going to be, let's see, positive and positive. And it's a positive value, so it's going to look like this. And it's going to be equal to 4.6875 megapascals. All right. Now on to solving our principal stresses. The equation for principal stresses is as follows. Sigma x over 2 plus or minus r, with r being equal to the square root of sigma x over 2 squared plus tau xz in this case squared, because we're on the xz plane. This is equal to, plug it in, 24.3 megapascals over 2 squared plus tau, which is 4.6875 megapascals. This is also squared. And the whole thing is square rooted. This becomes 13.058 megapascals. All right. Tau max equals R from the Mohr circle. So tau max equals 13.058 megapascals. Okay. Let's see. Sigma x over 2 equals, or actually, let's solve it like this. Sigma 1 equals 24.373 megapascals over 2 plus 13.058 megapascals. So sigma 1 equals 25.25 megapascals. That's one of our answers. There we go. Oh, looks like I got the 2 in there. It's okay. And then sigma 2. So this is our maximum and our maximum principal stress in the positive direction. Then let's see what our minimum stress is. And that's going to be equal to 24.373 over 2 megapascals minus 13.058 megapascals, which gives us a sigma 2, our second principal stress, of negative 0.8704 megapascals. Those are our 2 answers. There are 3 answers, but that is how you solve a combined loading problem. Just to recap, you find the resultant forces at the cut plane and the moments. Then you, I think it's easier to find the area of the cut plane and the 2 inertias around the axes that the cut plane's in. And then you take each one and then you solve for each one of the forces or moments and find out what it creates. For fx, it's axial. Mx is 0. Transverse, but these 2 we found out turn out to be 0. And yeah, I will. Oh, I guess I have to show my face this way. But I'm Brandon Lipscomb, red ID 821316581. All right, this is it.